Few periods in Earth's history captured the attention of scientists, and the public quite liked the Jurassic era. It was an age when giant dinosaurs became the dominant animals across vast landscapes. Powerful marine reptiles patrolled ancient seas, and winged reptiles crossed skies above dense forests that stretched for great distances. Beneath these thriving ecosystems, the planet itself was undergoing major transformation as continents gradually drifted apart and new environments emerged. Life was expanding into new forms, ancient lineages were evolving, and the foundations of future ecosystems were being established. A major shift in Earth's natural history began at the point where the Jurassic Period started following the ending stage of the Triassic Period. This change was not a single instant event, but a long transition, shaped by gradual environmental adjustment, biological loss, and the slow rebuilding of living systems across land and sea. The boundary between these two periods is strongly connected to a major extinction phase that affected life globally, where many species disappeared and surviving organisms became the foundation for new ecological development. The early Jurassic world formed through continuous changes in atmosphere, oceans, climate patterns, and biological activity that unfolded over extended time. During the final stages of the Triassic period, Earth experienced intense environmental stress that affected almost every region. Large volcanic events released significant amounts of gases into the atmosphere, especially carbon dioxide, which altered the balance of atmospheric composition. These changes influenced global temperature conditions and affected how heat was distributed across the planet. As atmospheric conditions changed, ocean systems also began to shift. Water chemistry in many regions was affected by increased carbon levels, which changed acidity and oxygen availability in marine environments. These conditions placed pressure on marine organisms that depended on stable oxygen levels and balanced chemical conditions. At the same time, land environments also experienced disruption. Plant communities that had been stable in earlier stages of the Triassic period were affected by changes in rainfall patterns and temperature variation. Soil moisture levels changed in different regions, which influenced plant growth and survival. As vegetation declined in some areas, the animals that depended on those plants also experienced reduced resources. These combined effects led to widespread biological loss across ecosystems both on land and in oceans. The end result of these processes was a major reduction in biodiversity before the beginning of the Jurassic period. As the transition into the Jurassic period began, environmental conditions started to shift again, but in a way that supported recovery rather than further decline. Surviving species from the extinction phase began to expand into areas where ecological pressure had been reduced. This expansion was gradual and depended on the slow stabilization of environmental systems. Marine ecosystems were among the first to show signs of recovery. Microscopic organisms in ocean water began to increase in number. These organisms formed the base of marine food systems and supported the return of larger marine life. Plankton populations became more stable over time, and their presence helped rebuild nutrient cycles in the oceans. These cycles involved the movement of nutrients through different layers of marine environments, supporting growth and reproduction of various organisms. As plankton communities expanded, they provided food sources for small marine animals, which then supported larger predators. This step-by-step rebuilding process allowed ocean ecosystems to regain structure over long periods. Marine reptiles also became more visible in early Jurassic oceans. Groups such as ichthyosaurs and plesiosaurs occupied ecological roles that involved movement through open waters and coastal regions. Their presence helped re-establish predator-prey relationships within marine environments. Fish populations also began to diversify again, filling ecological roles in different depth zones of the ocean. Some species lived near the surface, while others adapted to deeper or coastal waters, contributing to a more complex marine structure. Reef systems in shallow marine areas also began to recover during this time. Organisms capable of producing calcium-based structures contributed to the formation of solid frameworks on the seafloor. Over time, these structures became habitats for many marine species. Sediment accumulation around reef systems helped stabilize these environments, allowing them to persist and grow. These marine habitats supported a wide range of organisms and increased the overall biological activity of coastal regions. On land, recovery followed a slower but steady pattern. Plant life played a central role in restoring terrestrial ecosystems. Early Jurassic vegetation included groups such as ferns, cycads, and conifers. These plants spread into areas where soil and climate conditions supported growth. As plants expanded, they contributed organic material to the soil through natural processes such as decay and leaf fall. This organic material helped improve soil structure and increased its ability to support further plant growth. Soil development became an important factor in the recovery of land ecosystems. Rocks underwent weathering due to environmental exposure, producing mineral particles that mixed with organic material. Over time, this combination formed soil layers capable of supporting root systems. As root systems expanded, they helped stabilize soil and reduce erosion in certain areas. This stability allowed vegetation to grow more consistently across landscapes. The expansion of vegetation also influenced atmospheric conditions. Plants absorbed carbon dioxide during growth and released oxygen as part of their biological processes. Over long periods, this contributed to changes in atmospheric composition. These changes supported the development of more stable environments for terrestrial animals. The interaction between plant growth and atmospheric conditions became an important factor in ecosystem development during the early Jurassic stage. Animal life on land also began to diversify during this period. Early dinosaur groups became more widespread across different environments. These animals occupied various ecological roles, including plant-eating forms and meat-eating forms. Their presence added complexity to terrestrial ecosystems as they interacted with plant communities and other animals within shared environments. These interactions contributed to the structure of food systems on land. Other vertebrate groups were also present during this time. Small early mammals existed alongside dinosaurs. These mammals were generally small in size and occupied ecological roles that involved feeding on insects and small food sources. They were active in different environments, including forested regions and areas near rivers and lakes. Their presence added additional layers of biological activity to terrestrial ecosystems. Freshwater environments also underwent recovery. Rivers, lakes, and floodplains became important areas for biological development. Fish and amphibians repopulated these waters, while aquatic invertebrates contributed to nutrient cycles within freshwater systems. River movement transported sediments from land into lower areas, forming floodplains that supported vegetation growth. These environments provided habitats for a wide range of organisms and supported interactions between aquatic and terrestrial systems. Climate conditions during the early Jurassic period were influenced by ongoing volcanic activity and changes in atmospheric composition. Temperature levels varied across different regions, and rainfall patterns also shifted over time. Some regions experienced increased moisture, which supported dense plant growth, while other regions had more limited vegetation due to lower rainfall. These differences contributed to variations in ecosystem development across the planet. Ocean chemistry continued to change during this recovery phase. Carbon levels in seawater influenced chemical balance and affected organisms that relied on calcium-based structures. Over time, marine organisms adapted to these conditions, and biodiversity began to increase again. Nutrient cycling in oceans became more efficient as biological systems stabilized. This allowed marine ecosystems to support a wider range of life forms. The structure of ecosystems during the early Jurassic period involved developing connections between organisms and their environments. In terrestrial systems, plants formed the foundation of ecological networks. Herbivorous dinosaurs depended on vegetation for food, while carnivorous species fed on other animals. Insects played roles in decomposition and plant interactions. These relationships contributed to the overall organization of land ecosystems. In marine systems, plankton formed the base of food chains. Small organisms fed on plankton, and larger organisms fed on smaller ones. This structure supported a layered system of energy movement through marine environments. Reef systems provided stable habitats for many organisms, allowing for increased biological interaction in shallow waters. These ecosystems developed through continuous biological activity over long periods. Geological processes also influenced the development of early Jurassic ecosystems. Tectonic movement gradually changed the arrangement of continents and ocean basins. These movements affected ocean circulation patterns and influenced climate conditions across different regions. Volcanic activity continued in some areas, releasing gases that influenced atmospheric composition. These geological changes interacted with biological systems and shaped environmental conditions. Sediment formation played a role in shaping both marine and terrestrial environments. On land, weathering of rocks produced materials that formed soil. In oceans, sediments accumulated on the sea floor, creating layers that preserved biological material and influenced habitat structure. Rivers transported sediments from land to sea, linking terrestrial and marine systems through continuous movement of materials. Fungal organisms contributed to ecosystem recovery by breaking down organic matter and recycling nutrients into the soil. This process supported plant growth and helped maintain soil fertility. Microorganisms in both soil and water environments played essential roles in nutrient cycling. These organisms ensured that nutrients continued to move through ecosystems, supporting biological activity at multiple levels. Insect populations expanded during the early Jurassic period. These organisms occupied various ecological roles, including feeding on plants, decomposing organic matter, and interacting with other animals. Some insects lived in close association with vegetation, feeding on plant tissues and contributing to ecological interactions within plant communities. Their activity influenced plant development and ecosystem structure. Early mammals coexisted with dinosaurs during this period. These mammals were generally small and adapted to specific ecological niches. Their behavior often involved nighttime activity and feeding on insects or small food sources. They lived in environments that included forests, riverbanks, and areas with dense vegetation. Their presence contributed to the diversity of terrestrial ecosystems. Marine life continued to expand in variety and distribution. Ammonites became widely distributed across ocean environments. These organisms had coiled shells and lived in different marine habitats. They participated in marine food systems as both predators and prey. Belemnites also appeared and contributed to marine diversity. These organisms added to the complexity of ocean ecosystems during the early Jurassic stage. Sea level changes influenced coastal environments during this time. Variations in sea level created shifting boundaries between land and sea. Coastal ecosystems developed in response to these changes, supporting organisms adapted to shallow marine conditions. These environments allowed for interaction between land-based and marine systems, contributing to biological exchange across regions. Atmospheric gas exchange between oceans, land and living organisms played a role in regulating environmental conditions. Oxygen and carbon dioxide moved through biological and geological systems, supporting processes such as respiration and photosynthesis. These cycles contributed to the balance of atmospheric composition over time. The arrangement of continents influenced environmental patterns across the planet. Landmasses affected ocean currents and wind movement, which in turn influenced climate conditions. These patterns created differences in temperature and rainfall across regions, shaping the development of ecosystems in different locations. Marine gateways allowed movement of organisms between ocean regions, supporting biological distribution. Vegetation types in early Jurassic land environments were dominated by seed-producing plants that did not rely on flowers. These plants formed forested areas in suitable regions and contributed to the structure of terrestrial ecosystems. Some areas supported dense plant growth, while others had more open vegetation depending on environmental conditions. Seed dispersal and spore production allowed plants to spread across land surfaces. Ecological systems continued to develop through interactions between biological and geological processes. Plant growth influenced soil formation, while volcanic activity influenced atmospheric conditions. These interactions affected climate and ecosystem stability. Marine and terrestrial systems developed alongside each other, with nutrients and organisms moving between environments through rivers and coastal zones. Predator-prey relationships in marine environments became more structured as biodiversity increased. Large marine reptiles occupied higher positions in food systems, feeding on fish and other marine organisms. Fish populations diversified into different ecological roles, contributing to complexity in ocean ecosystems. These relationships supported the development of stable marine food networks. River systems continued to play a key role in transporting nutrients and sediments. These materials supported biological productivity in both freshwater and marine environments. Estuarine zones, where freshwater and saltwater mixed, supported high levels of biological activity. These areas provided habitats for organisms adapted to changing environmental conditions. The recovery and development of ecosystems during the early Jurassic period involved continuous biological activity across land and sea. Organisms adapted to changing environments, and ecological systems became more structured over time. These developments occurred through ongoing interactions between living organisms, geological processes, and atmospheric changes that shaped the early stages of the Jurassic world. During the period of the Jurassic world, the arrangement of land and water on Earth was undergoing steady and continuous change, shaped by movements within the planet's crust that acted over very long spans of geological time. Large land areas were not positioned in the separated form seen in later periods. Instead, most land existed within one connected mass that covered a vast portion of the planet's surface. This arrangement influenced where shallow seas formed how deep ocean basins expanded, and how new coastlines began to appear in different regions. The supercontinent known as Pangaea occupied a central role in this arrangement. It contained nearly all major continental landmasses joined together into one continuous structure. The internal regions of this landmass were far from ocean influence in many places, while outer margins met extensive ocean waters. The shape of this supercontinent was not uniform. It had curved edges, inward bends, and long coastal stretches that bordered surrounding seas. The surrounding water bodies included a broad ocean system that later geological studies identify as the Panthalassic Ocean, which covered most of the planetary surface that was not occupied by land. Within the interior of Pangaea, dry land conditions dominated many regions. Large desert zones existed due to the distance from ocean moisture sources. These dry regions extended over wide areas where rainfall was limited. In other regions closer to coastal zones, seasonal moisture reached inland areas, allowing more varied plant growth. The distribution of environments was closely linked to how far a location stood from ocean margins, and how atmospheric circulation moved moisture across the supercontinent. During the Jurassic interval of geological time, which occurred in the span beginning in the early part of the period, measured in tens of millions of years after the end of the previous Triassic interval, and continuing through the middle portion of the Mesozoic era, the structure of Pangaea began to change. The crustal plates beneath the supercontinent slowly shifted due to internal planetary forces. These movements caused the landmass to develop zones of weakness where stretching and thinning of the crust occurred. Over time, these zones developed into early rift systems where land began to separate. The earliest stages of continental separation did not involve sudden movement. Instead, the crust gradually pulled apart in long, linear regions. These regions developed fractures that extended across large distances. Magma from beneath the crust moved upward into these fractures, creating new igneous rock formations. These processes marked the beginning of new ocean basin formation in certain areas, where land separation progressed further. One of the major regions affected by early separation was located between what would later become the northern landmasses of Laurasia and the southern landmasses of Gondwana. Although these later continental names refer to configurations that became clearer after continued separation, during the Jurassic interval, the distinction between these large regions was still developing. The central zones of Pangaea began to show signs of internal division, where rifting activity created elongated basins filled with sediment and volcanic material. The position of continents during this time influenced global ocean circulation patterns. Because most land remained joined, ocean currents moved around the outer edges of the supercontinent and through narrow internal seaways where rifts had opened. These water movements carried heat across different regions of the planet. The distribution of warm and cooler waters affected marine environments along continental margins. Coastal zones along Pangaea experienced active geological change. In some areas, subsidence occurred, where the land slowly sank due to crustal stretching. This sinking created shallow marine environments that allowed seawater to flood previously dry regions. Sediments accumulated in these shallow basins, forming layered deposits over long periods. In other coastal regions, uplift occurred due to tectonic pressure, raising land above sea level and altering shoreline positions. The early stages of continental separation were closely linked to the formation of rift valleys. These rift systems developed where the crust was being pulled apart. The valleys often formed long linear depressions that extended through large sections of the supercontinent. Volcanic activity was common in these regions due to magma rising through fractures in the crust. Lava flows spread across the surface and cooled into solid rock layers that became part of the evolving geological structure. The interior climate of Pangaea was strongly influenced by its size and shape. Because of the extensive land coverage, atmospheric circulation patterns developed that transported dry air across large regions. Moist air from ocean margins did not always penetrate deeply into inland zones. This resulted in areas where rainfall remained limited over long periods. Seasonal changes occurred, but the distribution of moisture remained uneven across the supercontinent. Vegetation during the Jurassic world adapted to these conditions. Plant life existed in regions where moisture was sufficient to support growth. Along coastal margins and near river systems, vegetation was more diverse and dense. Inland regions supported plant communities that could withstand dry conditions. The arrangement of plant life influenced the distribution of animal life, which followed the availability of vegetation and water sources. The early separation of continental masses influenced the development of new ecological regions. As rifts widened, isolated environments formed on either side of developing basins. These isolated regions began to experience differences in climate and environmental conditions. Over extended geological time, these differences contributed to the development of distinct biological communities in separated regions. The ocean surrounding Pangaea played an important role in regulating global environmental conditions. Because the ocean covered most of the planet, it acted as a major reservoir for heat distribution. Water movement along the edges of the supercontinent influenced temperature conditions on nearby land areas. Marine currents carried nutrients across long distances, supporting marine ecosystems along continental shelves. In regions where rifting progressed more strongly, narrow sea passages began to develop. These passages allowed marine waters to extend into interior zones of the supercontinent. Sediment deposition in these regions created layered formations that recorded the gradual transition from land to marine environments. The presence of these sediments provides evidence of changing shoreline positions over extended time intervals. The structural arrangement of Pangaea during the Jurassic interval was not static. Continuous movement of tectonic plates beneath the crust caused ongoing changes in the shape of the landmass. These movements were slow on a human time scale, but significant over geological durations. Crustal stretching, folding, and faulting occurred in different regions, contributing to the gradual fragmentation of the supercontinent. The early separation process involved the development of fault lines that extended through large portions of the crust. These faults created zones where rock layers shifted relative to each other. In some regions, blocks of crust moved downward, forming basins. In other regions, blocks moved upward, forming elevated areas. These structural changes influenced drainage patterns, river formation, and sediment transport across the land surface. The position of continents also influenced atmospheric circulation on a global level. Because the landmass extended across multiple climate zones, air movement patterns were shaped by temperature differences between regions. Warm air rose in equatorial zones while cooler air moved toward lower latitudes. These circulation patterns contributed to seasonal variations in rainfall distribution. Marine environments during the Jurassic period were closely connected to continental margins. Shallow seas developed along the edges of Pangaea where the land met ocean waters. These shallow marine zones supported sediment accumulation and provided environments where chemical processes influenced rock formation. The interaction between land and sea in these regions contributed to the development of complex coastal systems. The gradual opening of new ocean basins began in specific regions where rifting activity continued for extended periods. These basins filled with seawater as crustal separation increased. The formation of new oceanic crust occurred where magma rose and solidified beneath the ocean floor. This process contributed to the expansion of oceanic areas and the reduction of continuous land connectivity. Within the interior of Pangaea, large river systems developed that transported water across long distances. These rivers carried sediment from elevated regions to lower basins where deposition occurred. Over time, these sediment deposits formed layered rock formations that recorded environmental conditions. The direction and flow of these river systems were influenced by the topography created through tectonic activity. The early stages of continental fragmentation also influenced volcanic activity across the supercontinent. Magma movement beneath the crust increased in regions where the land was being stretched. Volcanic eruptions released material onto the surface, creating layers of basalt and other igneous rocks. These volcanic deposits became integrated into the evolving geological structure of the region. The arrangement of land and sea during the Jurassic world created conditions for ongoing environmental change. Coastal regions shifted position due to tectonic movement, while inland areas experienced gradual alteration in elevation and drainage patterns. The interaction between crustal movement and surface processes shaped the overall structure of the planet's surface. In the northern portion of Pangaea, the landmass that would later be identified as Laurasian regions began to show clearer signs of separation from southern regions. Rift systems expanded in certain zones, creating narrow basins that gradually filled with water. These early basins represented initial stages in the development of new oceanic divisions. In southern regions of Pangaea, the landmass that would later become part of Gondwanan areas also experienced tectonic stretching. Crustal deformation created zones of weakness where future separation would continue. These regions contained a mixture of stable land and active rift zones, where geological change was ongoing. The distribution of sediments during this time provides evidence of changing environmental conditions. In rift basins, sediments accumulated from surrounding highlands and from volcanic sources. These deposits formed layered sequences that reflect cycles of deposition over extended periods. The nature of these sediments indicates changes in water presence, erosion rates, and volcanic input. Oceanic circulation around Pangaea influenced the distribution of marine life in coastal regions. Nutrient-rich waters supported ecosystems along continental margins. The movement of water masses around the supercontinent affected temperature distribution in different marine zones. These conditions contributed to variations in marine habitat structure. The early separation of continents also influenced the formation of shallow inland seas in certain regions. Where rift basins sank below sea level, marine waters entered and formed restricted seaways. These environments experienced varying levels of salinity and sediment input from surrounding land. Over time, these conditions led to the development of distinct geological formations. The crustal dynamics during the Jurassic interval involved continuous interaction between tectonic plates. The movement of these plates caused pressure buildup in some regions and extension in others. This interaction resulted in alternating zones of compression and tension across the supercontinent. The effect of these forces were recorded in rock structures that show folding, faulting, and fracturing patterns. The position of continents during this period influenced long-term planetary heat distribution. Because land and sea were arranged in specific configurations, heat exchange between surface regions and the atmosphere followed distinct patterns. Ocean waters acted as major regulators of thermal energy, distributing heat across broad areas through circulation systems. The early fragmentation of Pangaea set the foundation for later continental arrangements. The initial rift zones that formed during the Jurassic interval continued to expand over time. These zones eventually developed into wider ocean basins, further separating landmasses and changing global geography. The processes that began during this period continued through later geological intervals, shaping the evolving structure of Earth's surface in ongoing phases that extended beyond the Jurassic world. The climate and weather of the Jurassic period existed under conditions that supported widespread warmth across the planet and stable atmospheric behavior over long spans of time. The air, oceans, land surfaces, and living environments were all influenced by steady patterns of heat distribution, moisture movement, and solar energy input. These conditions shaped how clouds formed, how rainfall appeared in different locations, and how seasonal cycles developed in various parts of the world. The structure of the atmosphere allowed consistent exchange of heat and moisture between oceans and land areas, and this created long-lasting climate states that influenced ecosystems across many regions of the planet. The arrangement of land masses at that time also influenced how air moved across the surface, how water evaporated from large water bodies, and how moisture returned to the ground through precipitation. The atmosphere carried water vapor in different amounts depending on location, and this affected cloud formation and rainfall activity in many zones. The oceans also played an important role in storing and distributing heat across the planet, helping to maintain steady environmental conditions over long durations. Global temperatures during the Jurassic period existed within a warm range that shaped both land and ocean environments. The air over most regions held significant amounts of heat energy, and this influenced surface conditions in many ways. Large portions of land experienced temperatures that supported continuous biological activity, soil development, and plant growth. The oceans also held warm water in many areas, and this warmth extended from surface layers into deeper parts of marine environments. The distribution of heat across the planet was affected by atmospheric circulation patterns that moved warm air across wide regions and helped maintain steady thermal conditions over long periods of time. Solar energy reached the surface consistently, and the atmosphere retained a large portion of this energy, allowing the planet to maintain warm conditions in many latitudes. Temperature levels in equatorial regions remained high throughout the year, with only small variations occurring during different periods. These regions received direct solar energy in a consistent manner, and this supported stable heat accumulation in both land and water surfaces. Tropical zones extended over wide areas, and these zones experienced continuous warmth in air and soil environments. Vegetation in these regions responded to stable thermal conditions, and soil processes occurred under constant heat exposure. Moisture in the air interacted with this warmth, leading to steady formation of clouds in many locations. In mid-latitude regions, temperature conditions remained moderate to warm, and seasonal variation in heat levels existed in a gentle form. Air movement from tropical zones carried warmth toward higher latitudes, distributing thermal energy across broad areas. These regions experienced periods where heat levels rose steadily during certain parts of the year and then stabilized during other periods. The ground surface in these areas absorbed heat during extended daylight periods, and this heat remained stored in soil layers for significant durations. Water bodies in these regions also retained warmth, and this influenced nearby land conditions. In polar regions, temperature conditions were not permanently frozen, and periods of warmth existed during extended parts of the year. Air circulation patterns carried warm air towards these regions, and this helped maintain liquid water in many areas. Ice formation occurred in limited zones and during specific intervals, but large areas remained free from long-lasting freezing conditions. The atmosphere in these regions held enough heat to support plant growth during favorable periods, and soil layers experienced cycles of moisture and warmth that allowed biological activity to continue. The distribution of heat across oceans played a central role in global temperature stability. Ocean water absorbed solar energy during daylight periods and stored this heat for long durations. This stored heat was gradually released into the surrounding atmosphere, helping to maintain steady air temperatures above ocean surfaces. Ocean currents moved warm water across different parts of the planet, carrying thermal energy from one region to another. These currents influenced coastal environments, where air temperature and moisture levels remained closely connected to ocean conditions. The atmosphere during the Jurassic Period contained significant amounts of water vapor, which influenced how heat was distributed. Water vapor absorbed and released heat energy as it moved through different layers of the atmosphere. This process helped regulate temperature levels across different regions of the planet. Cloud formation occurred when water vapor condensed in the atmosphere, and these clouds played a role in controlling how much solar energy reached the surface. Cloud cover also influenced nighttime conditions by reducing heat loss from the ground into the upper atmosphere. Rainfall patterns during the Jurassic Period developed through interactions between ocean evaporation, atmospheric circulation, and land surface heating. Water from oceans and large lakes evaporated into the atmosphere, forming moisture-rich air masses that moved across the planet. As these air masses traveled, they carried water vapor towards different regions, where cooling conditions allowed condensation to occur. This condensation formed clouds, which later produced rainfall when water droplets became heavy enough to fall to the surface. Rainfall occurred in many regions of the planet with varying levels of frequency and intensity, depending on atmospheric moisture content and air movement patterns. Areas located near large water bodies received steady moisture input from evaporation processes. These regions experienced repeated cycles of cloud formation and precipitation. Land areas located farther from oceans also received rainfall, though the timing and distribution of precipitation depended on the movement of moist air masses across the landscape. In tropical regions, rainfall activity remained frequent due to continuous evaporation from nearby water surfaces and consistent atmospheric moisture levels. Warm air in these regions held large amounts of water vapor, and this vapor rose into higher layers of the atmosphere where cooling conditions led to cloud formation. Rainfall events occurred when cloud systems reached saturation, releasing water back to the surface in repeated cycles. Soil in these regions remained moist for long periods, and water flowed through river systems that carried precipitation from elevated areas toward lower terrain. In mid-latitude regions, rainfall patterns followed seasonal cycles influenced by changes in air circulation. Moist air masses moved into these regions at different times, bringing periods of precipitation followed by intervals of reduced rainfall. Cloud systems formed along boundaries where different air masses interacted, and these systems produced rainfall across wide areas. Rivers and lakes in these regions received water from both direct precipitation and runoff from surrounding land surfaces. In polar regions, rainfall occurred during warmer periods when atmospheric moisture was present and temperatures allowed liquid precipitation. Snowfall also occurred in areas where temperatures supported ice formation in clouds. Precipitation in these regions contributed to seasonal water cycles that influenced soil moisture and surface conditions during warmer intervals. When conditions allowed, meltwater from snow and ice contributed to streams and surface water flow. The movement of moisture across the atmosphere created continuous cycles of evaporation, condensation, and precipitation. Ocean surfaces provided a constant source of water vapor through evaporation, especially in regions where solar energy input remained strong. This vapor rose into the atmosphere and moved with air currents towards different parts of the planet. Cooling of air masses at higher altitudes allowed water droplets to form, which later combined into larger droplets that fell as rainfall. This process repeated continuously, maintaining moisture distribution across land and sea. Seasonal conditions across different regions of the planet followed patterns influenced by solar energy distribution, atmospheric circulation, and the tilt of the planet's axis. These seasonal conditions did not produce abrupt changes in temperature or precipitation, but instead formed gradual cycles of variation in environmental conditions. The movement of the planet around the Sun created shifts in sunlight exposure in different latitudes, which influenced air temperature, moisture levels, and cloud formation patterns. In equatorial regions, seasonal variation in weather conditions remained present, but appeared in subtle forms. The position of the Sun relative to these regions changed during different parts of the year, but the overall energy input remained consistently strong. Rainfall patterns in these regions followed cycles influenced by atmospheric moisture movement rather than strong temperature shifts. Periods of increased cloud formation occurred when moisture-laden air converged in certain areas, leading to repeated rainfall events. Soil moisture levels remained relatively stable across different seasonal phases, and water bodies maintained steady levels of flow and replenishment. In mid-latitude regions, seasonal cycles influenced both temperature and rainfall patterns in more noticeable ways. During certain periods of the year, sunlight exposure increased, leading to extended periods of warmth in land and water surfaces. During other periods, sunlight exposure decreased, leading to cooler atmospheric conditions and reduced evaporation rates. These changes influenced the timing and distribution of rainfall events, with wetter periods occurring when atmospheric moisture was more abundant and drier periods occurring when moisture levels were reduced. Vegetation and soil conditions responded to these cycles through changes in growth rates and water retention processes. In polar regions, seasonal conditions were strongly influenced by variations in sunlight duration. During periods of extended sunlight, surface temperatures increased enough to allow liquid water to exist in many areas, and biological activity became more active during these times. During periods of reduced sunlight, surface conditions became colder, and ice formation occurred in many locations. Atmospheric moisture during these periods moved through cycles of freezing and melting depending on temperature conditions. Snow accumulation and melting followed these seasonal changes, influencing surface water availability and soil moisture content. Atmospheric circulation patterns connected all regions of the planet and influenced seasonal conditions across wide areas. Large air movement systems transported heat and moisture between equatorial, mid-latitude, and polar regions. These movements created repeating cycles of cloud formation and rainfall that affected land surfaces in different ways, depending on location. Ocean-atmosphere interactions played a significant role in regulating these seasonal patterns, as ocean surfaces stored and released heat energy over extended periods. Land surface conditions also influenced seasonal behavior through interactions with sunlight and moisture. Soil absorbed heat during periods of strong sunlight exposure and released heat during periods of reduced sunlight. This process affected air temperature near the ground and influenced the formation of clouds and rainfall. Vegetation in many regions also contributed to moisture movement through the release of water vapor into the atmosphere, which added to cloud formation processes during different seasonal phases. The structure of seasonal cycles across the planet reflected continuous interactions between solar energy, atmospheric motion, ocean behavior, and land surface processes. These interactions created repeating patterns of temperature variation, rainfall distribution, and atmospheric moisture movement across different regions. The timing and duration of these patterns followed natural cycles linked to planetary movement and energy distribution across the surface. The oceans and seas during the Jurassic time were wide areas of water covering large parts of the planet's surface, and they changed in shape, depth, and reach over long spans of time. Large sections of land were slowly covered by marine waters in many regions, and this allowed seawater to extend into spaces that were previously dry land. These marine waters created broad environments where water remained shallow for long distances away from coastlines, forming extensive, shallow sea zones that became a central part of the global marine system during this time. The expansion of shallow seas happened through long processes of changes in the level of the ocean surface and movements of the Earth's crust. Parts of the land slowly sank in some regions, and in other regions the water level of the oceans rose gradually over long intervals. These changes allowed seawater to move over continental surfaces in a slow and steady way. As the water moved over land areas, it filled low regions first and then spread into surrounding zones that were at slightly higher ground levels. This process created wide, shallow marine environments that connected many coastal regions and inland basins. These shallow seas covered large continental margins and extended into the interior regions of some land masses. The water depth in these areas was not very deep in many places, and sunlight could reach much of the seabed. The presence of sunlight in these shallow marine zones allowed biological activity to be supported throughout the water column and along the seafloor. Sediments carried by rivers and coastal erosion entered these seas continuously, building layers of fine materials on the seabed. These sediments influenced the structure of the marine floor and affected how water moved through these regions. The movement of seawater within Jurassic oceans and seas followed patterns driven by wind activity, differences in water temperature, and variations in salt concentration. Large surface movements of water occurred over wide oceanic regions, and deeper water movements developed below the surface layers. Water in surface regions was influenced by atmospheric conditions, while deeper water movement was influenced by density differences caused by temperature and salt content variations. These movements created continuous circulation within ocean basins and connected different marine environments. In shallow seas, circulation patterns were often influenced by the shape of coastlines and the presence of landmasses that divided water bodies into smaller sections. Narrow marine passages allowed water to move between larger ocean areas and enclosed seas. These passages supported the exchange of water between different marine regions, allowing water properties such as temperature, salinity, and nutrient content to be redistributed over time. The movement of water through these channels played a role in maintaining continuous marine conditions across separated basins. Marine circulation also included vertical movement of water between surface layers and deeper layers. Surface water could move downward in some regions where it became denser, due to changes in temperature or salt concentration. In other regions, deeper water moved upward, bringing materials from the lower parts of the ocean toward the surface. This vertical movement allowed nutrients to be transported through different layers of the ocean, supporting biological activity at various depths. The mixing of water layers also influenced chemical conditions throughout marine environments. Ocean chemistry during this time was influenced by the balance of dissolved minerals, gases, and organic materials within seawater. Rivers carried dissolved substances from land into the oceans, and volcanic activity added additional chemical components to marine systems. These inputs contributed to the overall chemical composition of seawater and affected the conditions in which marine life existed. The chemistry of seawater varied across different regions depending on local inputs and the degree of water circulation. In shallow sea environments, chemical conditions were influenced strongly by the interaction between seawater and sediments on the seabed. Sediments released minerals into the water, and chemical reactions occurred between water and the materials deposited on the ocean floor. These interactions influenced the levels of oxygen and other dissolved substances within the water. In areas where water movement was limited, chemical conditions could develop distinct characteristics based on local biological activity and sediment composition. The availability of oxygen in marine waters played an important role in shaping ocean chemistry. Oxygen entered seawater from the atmosphere at the surface and was transported into deeper layers through circulation processes. In regions where circulation was strong, oxygen could reach deeper parts of the ocean more effectively. In areas where circulation was limited, oxygen levels could vary significantly between surface and deeper waters. These differences influenced the chemical balance of marine environments and affected biological processes throughout the water column. Carbon in the form of dissolved carbon compounds was also an important part of ocean chemistry. Carbon entered marine systems through river input, atmospheric exchange, and biological activity. Marine organisms contributed to carbon movement by absorbing and releasing carbon during their life processes. When organisms died, their remains contributed organic material to the seafloor, where chemical changes continued through decomposition processes. These processes influenced the distribution of carbon within marine systems and affected chemical conditions in both shallow and deeper waters. Salinity levels in Jurassic oceans and seas were not uniform across all regions. Areas with high evaporation rates could develop higher salt concentrations, while regions with significant freshwater input from rivers could have lower salt levels. The movement of water through ocean circulation helped to redistribute salt across marine environments, but local variations remained present due to environmental conditions. These variations in salinity influenced water density and contributed to the movement patterns of marine circulation. Nutrient distribution within marine systems played a key role in supporting biological activity in Jurassic oceans and seas. Nutrients entered the water through river discharge, coastal erosion, and volcanic sources. Once in the oceans, these nutrients were transported by water movement across different regions. Areas with active circulation often received a continuous supply of nutrients, while more isolated marine regions depended on local sources and slower transport processes. Nutrient availability influenced the presence and activity of marine organisms across different marine zones. The interaction between ocean chemistry and marine life created continuous cycles of material exchange within Jurassic seas. Marine organisms absorbed chemical elements from seawater for growth and development. When these organisms produced waste or died, their remains contributed to the chemical composition of sediments and seawater. This exchange influenced the balance of chemical elements in the ocean and maintained ongoing processes of transformation within marine systems. The shallow seas also served as areas where chemical and physical conditions changed gradually across space and time. Water movement through these areas carried dissolved materials and suspended particles that influenced the clarity and composition of seawater. Sediment accumulation on the seafloor affected chemical exchanges between water and solid materials. These processes created continuous interaction between physical movement of water and chemical changes within marine environments. Marine circulation patterns also played a role in distributing heat energy within Jurassic oceans and seas. Warm surface waters moved across large distances, while cooler waters occupied deeper regions or moved towards different areas depending on circulation pathways. The movement of heat through water influenced chemical reactions within the ocean and affected the solubility of gases such as oxygen and carbon dioxide. These interactions contributed to the overall chemical structure of marine environments. The structure of ocean basins influenced how water moved within Jurassic seas. Some basins were wide and open, allowing large-scale circulation of water, while others were more restricted, limiting water exchange between regions. The shape of the seafloor, the presence of underwater ridges, and the distribution of continental masses all affected the movement of seawater. These structural features guided circulation pathways and influenced how chemical substances were distributed across marine environments. In regions where shallow seas extended over continental areas, the interaction between land and sea created zones where freshwater and seawater mixed continuously. Rivers entering these seas carried sediments and dissolved materials that altered local chemical conditions. The mixing of freshwater and seawater influenced salinity and nutrient levels, creating variations in water chemistry across short distances. These zones of interaction were dynamic and continuously influenced by changes in river flow and marine movement. The chemistry of Jurassic oceans and seas also reflected long-term exchanges between the ocean and the Earth's crust. Chemical elements were transferred between seawater and seafloor sediments through processes of deposition and dissolution. Over time, these exchanges contributed to the accumulation of mineral deposits on the ocean floor and influenced the chemical composition of seawater. Volcanic activity beneath or near ocean basins added additional chemical inputs, affecting the balance of elements in marine systems. The continuous movement of seawater through circulation systems allowed chemical conditions to be redistributed across large areas of the ocean. This redistribution meant that changes in one region could influence conditions in distant marine areas over time. The mixing of water masses supported the movement of dissolved substances and maintained ongoing chemical interactions within ocean systems. These processes contributed to the complexity of marine chemistry during the Jurassic time. Within shallow seas, biological activity interacted closely with chemical conditions in seawater. Organisms extracted dissolved elements from water for biological processes and returned materials to the environment through waste and decomposition. This exchange influenced the chemical structure of seawater and contributed to sediment formation on the seafloor. The accumulation of organic and inorganic materials in sediments created layers that reflected ongoing chemical and biological activity within marine environments. The relationship between marine circulation and ocean chemistry also influenced the distribution of gases within seawater. Oxygen and carbon dioxide moved between the atmosphere and the ocean surface, and circulation processes distributed these gases throughout different water layers. Areas with strong circulation had more uniform distribution of gases, while areas with limited circulation showed variation in gas concentrations between surface and deeper waters. These patterns affected chemical reactions within marine systems. The movement of seawater through narrow marine passages allowed for the exchange of chemical properties between different ocean regions. Water passing through these passages carried dissolved substances that influenced the chemistry of connected basins. Over time, this exchange contributed to the development of chemical continuity between distant marine environments. These passages served as pathways for both physical movement and chemical distribution within Jurassic oceans and seas. Sediment composition on the ocean floor played an important role in shaping ocean chemistry. Different types of sediments interacted with seawater in different ways, releasing or absorbing chemical elements depending on their composition. Organic-rich sediments influenced oxygen levels in surrounding water, while mineral-rich sediments contributed dissolved elements to seawater. These interactions created chemical variation across different parts of the seafloor. The continuous input of materials from land into shallow seas through rivers influenced the chemical balance of marine environments. These inputs included dissolved salts, minerals, and organic matter carried by water flow from continental regions. Once in the marine system, these materials were distributed by circulation and affected chemical conditions across different areas of the ocean. The interaction between land-derived materials and marine processes remained active throughout this time. Marine chemistry was also influenced by the exchange of gases between seawater and the atmosphere. The surface of the ocean allowed gases to move between air and water, and this exchange affected the chemical composition of both systems. The movement of gases was influenced by water temperature, circulation patterns, and biological activity. These processes contributed to ongoing chemical changes within Jurassic oceans and seas. The structure of shallow marine environments allowed sunlight to penetrate into the water column, which influenced chemical processes within the upper layers of the ocean. Light-driven reactions affected the behavior of dissolved substances and supported biological processes that contributed to chemical cycling. These processes were closely connected to the physical structure of shallow seas and the movement of water within them. Plant life during the Jurassic time was shaped by living systems that spread across land in a wide and steady way, filling many environments with green vegetation that followed the patterns of climate, soil conditions, and changing landscapes. The land surface supported plant groups that were mostly seed-producing plants that did not rely on flowers, and these plants formed the main structure of forests and open plant communities. The most widespread plant group during this time was the gymnosperms, which are seed plants that produce seeds without enclosing them inside fruits. These plants formed the central part of most terrestrial ecosystems and were present in many regions across the planet, from warmer lowland areas to cooler elevated zones. Their ability to reproduce through exposed seeds and their capacity to grow in different soil conditions allowed them to remain stable across long periods of time. Gymnosperms included several major plant types, and each type had its own structure and way of growing. Among them, conifers were one of the most widespread groups. Conifers produced seeds inside woody cones, and their leaves were usually shaped in narrow or needle-like forms. These leaves helped the plants reduce water loss, which allowed them to survive in areas where rainfall changed throughout the year or where dry conditions appeared for parts of the seasons. Conifers formed large forested areas in many regions and grew in both dense and open formations depending on soil depth, moisture levels, and temperature stability. Their trunks were often tall and straight, and their branching patterns allowed them to reach sunlight above surrounding vegetation. Cycads were another important group of gymnosperms that existed during this time. These plants had thick, often short trunks, and a crown of stiff divided leaves that grew from the top. Cycads were slow-growing plants, and many of them lived in environments where light was available, but soil nutrients were limited or unevenly distributed. Their root systems were sometimes associated with microorganisms that helped in nutrient absorption, allowing them to survive in conditions where other plants might struggle to maintain steady growth. Cycads were present in both inland regions and areas closer to ancient coastlines, and they formed clusters in suitable environments where temperature and moisture levels remained steady for long periods. Ginkgos were also part of the gymnosperm group during this period. These plants had fan-shaped leaves with veins spreading out in a pattern across the leaf surface. Ginkgo trees were capable of living in a range of environmental conditions, and they could continue growth even when seasonal changes affected surrounding plant life. They were not as widespread as conifers, but they were present in many regions and contributed to forest structure in areas where they grew. Their leaves often changed with seasonal shifts, and they produced seeds that were not enclosed within fruits, following the general reproductive pattern of gymnosperms. The dominance of gymnosperms during the Jurassic was linked to their reproductive structure, growth patterns, and adaptability to land environments that were still undergoing long-term geological changes. The land surface at this time was divided into large regions with different climate conditions, and plant life had to adjust to variations in rainfall, temperature, and soil development. Gymnosperms were able to maintain stable populations across these regions because their seeds could develop without needing complex pollination systems involving animals or flowers. Wind played a major role in the movement of pollen, and this allowed reproduction to occur over wide areas. Plant life was not evenly spread across all regions, and different areas supported different plant communities based on local environmental conditions. In some regions, dense forest systems formed where moisture levels were sufficient and where soil layers could support continuous plant growth. These forest systems included multiple layers of vegetation, with taller conifers forming upper layers and lower-growing cycads and other gymnosperms filling spaces beneath them. In other regions where rainfall was lower or seasonal variation was stronger, plant communities were more open, with scattered trees and smaller clusters of vegetation separated by areas of exposed ground. The structure of Jurassic forests varied based on available resources and environmental stability. In wetter regions, plant growth was continuous, and vegetation covered large areas with overlapping canopies formed by tall gymnosperms. These canopies reduced direct sunlight reaching the ground, creating shaded environments beneath them. In such shaded areas, plants adapted to lower light levels were able to survive, including younger plants and smaller species. The presence of thick vegetation layers influenced soil moisture retention and helped maintain local humidity levels, which supported further plant growth. In regions where rainfall was less consistent, plant life adjusted through spacing and reduced density. Trees and other gymnosperms were distributed in patterns that reflected water availability and soil depth. Some areas supported seasonal growth cycles where plant activity increased during wetter periods and slowed during drier times. Conifers were especially capable of surviving in these conditions because their leaf structures limited water loss, and their root systems could access moisture from deeper soil layers. The spread of ginkgos in these environments was influenced by their ability to tolerate changing conditions. They could grow in both sheltered and more open areas, and their leaf structure allowed them to continue photosynthesis under varying light conditions. Although they were not the most widespread plant group, their presence added to the diversity of plant life in many regions where they were established. The global distribution of plant life during the Jurassic was influenced by the arrangement of landmasses and the movement of climate systems across the planet. Large connected land areas allowed plant groups to spread across wide regions without major physical barriers. This allowed gymnosperms to expand their presence over long distances and establish populations in many different ecological zones. Over time, these plant groups adapted to local conditions while maintaining their general structural characteristics. Soil development during this time also played a role in plant distribution. As plant life became more established in different regions, organic material from fallen leaves and plant remains contributed to soil formation. This process supported further plant growth by improving soil structure and nutrient availability. In regions with continuous plant cover, soil layers became more stable and supported long-term plant communities. In areas with less vegetation cover, soil development was slower and more affected by erosion and seasonal changes. Moisture availability was a major factor in determining where dense forests formed. Areas with consistent rainfall supported continuous plant growth and allowed large forest systems to develop. In these regions, gymnosperms grew in multiple layers and formed extensive vegetation cover. In areas where rainfall was uneven, plant growth adapted through spacing and reduced density, allowing plants to survive in conditions where water supply changed over time. Temperature conditions also influenced plant distribution. Warm conditions supported rapid plant growth and allowed many gymnosperms to expand their range into new areas. In cooler regions, plant growth continued, but at a slower rate, and plant communities adjusted through structural changes such as reduced leaf size or slower reproductive cycles. These adjustments allowed plants to maintain long-term survival across different environmental zones. The reproduction of gymnosperms during this time relied on seed production and wind-based pollen movement. Male reproductive structures released pollen into the air, which was then carried over distances before reaching female reproductive structures. Once fertilization occurred, seeds developed and were released into the environment. These seeds could remain dormant for periods of time before germinating when conditions became suitable. This reproductive system allowed plant populations to persist even when environmental conditions changed temporarily. Conifers produced seeds inside cones that developed on branches. These cones protected developing seeds until they were mature enough to be released. Once released, seeds could be transported by wind or other environmental processes, allowing new plant growth to occur in different locations. The structure of conifer seeds and cones contributed to the spread of these plants across many regions. Cycads produced reproductive structures that were often associated with specific environmental conditions. Some cycads relied on wind for pollen movement, while others may have interacted with insects that transferred pollen between plants. The development of seeds allowed cycads to establish new growth in suitable habitats where conditions supported their slow growth patterns. Ginkgos produced seeds that were released from reproductive structures and could develop in suitable soil conditions. Their reproductive cycle allowed them to maintain populations in areas where environmental conditions remained stable enough for seed development and plant growth. The arrangement of forests during this time created a wide range of plant environments across the land surface. Some forests were dense and continuous, while others were more open and scattered. In dense forest systems, light penetration to the ground was reduced, influencing which plants could grow beneath taller vegetation. In more open systems, sunlight reached the ground more directly, allowing a wider distribution of smaller plants and young tree growth. Plant communities also interacted with water systems. Roots of gymnosperms helped stabilize soil and influenced water movement through the ground. In areas with dense vegetation, water retention in soil increased, supporting continued plant growth. In areas with less vegetation, water movement through soil was more rapid, affecting plant distribution patterns. The spread of plant life across different regions created a continuous system of vegetation that supported many forms of terrestrial life. Plant material provided organic matter to soils, which contributed to nutrient cycles that supported further plant growth. Fallen leaves and plant debris accumulated in many areas, slowly breaking down and becoming part of the soil structure. Over long periods, plant communities adjusted to gradual changes in environmental conditions. Gymnosperms remained central to these systems due to their ability to survive across a wide range of environments and their capacity to reproduce without requiring specialized conditions. Conifers, cycads, and ginkgos each contributed to the structure of vegetation across different regions, forming the main plant groups that shaped terrestrial landscapes during this time. The distribution of forests continued to reflect environmental factors, such as rainfall, temperature, soil type, and land elevation. Each region supported plant communities that developed according to local conditions, and these communities remained stable over long periods when conditions stayed consistent. Where conditions changed, plant communities adjusted through shifts in density, growth patterns, and reproductive timing. Plant life during this period formed an interconnected system across land areas, with gymnosperms providing the main structural framework for vegetation. Their presence in forests and open landscapes shaped the distribution of plant material, soil formation processes, and ecological stability across many regions of the planet. The rise of dinosaur dominance during the Jurassic period was a long and steady process that unfolded after major changes in life on Earth that began at the end of the Triassic period. This rise did not happen suddenly or in a single moment. It developed over millions of years as dinosaur groups increased in number, spread into many environments, and became more varied in body form, feeding style, and way of living. The world at that time was changing in climate, land structure, and available ecosystems, and these conditions allowed dinosaurs to expand into many ecological roles. Over time, dinosaurs became some of the most visible and widespread land animals across the planet, occupying many different habitats and forming large and diverse populations. Dinosaur diversification was one of the most important parts of this rise. Diversification means that a single group of organisms develops into many different forms that are adapted to different ways of living. Early dinosaurs first appeared in the late Triassic period, but they were not yet the dominant land animals. They existed alongside many other reptile groups, including large archosaurs and other early reptiles that shared land environments. As time moved into the Jurassic period, dinosaur groups began to split into many branches. These branches developed different body shapes, sizes, feeding habits, and movement styles. Some dinosaurs became small and fast-moving animals that relied on speed and agility. Others grew into large, heavy-bodied herbivores that moved slowly and fed on plants. There were also carnivorous dinosaurs that developed strong jaws and sharp teeth for hunting or scavenging other animals. This diversification was supported by genetic variation within dinosaur populations. Over many generations, small changes in body structure and function appeared. Some dinosaurs developed longer necks that allowed them to reach vegetation in higher or lower positions. Others developed stronger hind limbs that supported faster movement. In some groups, forelimbs became reduced or specialized for grasping or balancing. Teeth also changed in different lineages, with some dinosaurs developing blade-like teeth for cutting plant material or flesh, while others developed spoon-shaped teeth suited for stripping vegetation. These differences allowed dinosaur groups to reduce direct competition for the same food sources and allowed many species to live in the same general region while using different resources. Dinosaur diversification also involved changes in reproductive and growth patterns. Dinosaurs laid eggs, and nesting behavior became an important part of their life cycle. Some species laid eggs in clusters in protected areas, while others likely used open nesting sites. Hatchlings in many species were small and grew quickly, which allowed populations to recover and expand more rapidly in favorable conditions. Growth rates varied between species, with some dinosaurs reaching adult size in a relatively short time, and others taking many years to reach full size. These differences in growth patterns helped different dinosaur groups survive in different environments and adapt to varying levels of food availability and environmental stability. During the Jurassic Period, the number of dinosaur species increased significantly. This increase in species diversity allowed dinosaurs to occupy a wide range of ecological roles. New species appeared in different regions of the world as land areas were separated and connected in different ways due to slow continental movement. As land environments changed, isolated populations of dinosaurs developed unique features that distinguished them from other groups. Over time, this process led to a wide variety of dinosaur forms, each adapted to specific conditions such as forested areas, open floodplains, dry regions, and coastal environments. Ecological advantages played a major role in the rise of dinosaur dominance. Ecological advantages are traits or behaviors that allow a group of organisms to survive and reproduce more successfully in their environment. One of the most important advantages of dinosaurs was their ability to move efficiently on land. Many dinosaur species developed upright limb positions, which allowed their legs to support their body weight directly beneath them. This structure improved movement efficiency and allowed dinosaurs to travel longer distances while searching for food or escaping danger. This ability to move effectively across large areas of land helped dinosaurs expand into different habitats and access a wide range of resources. Another ecological advantage was related to feeding flexibility. Different dinosaur groups developed specialized feeding structures that allowed them to consume a variety of plant materials or animal prey. Herbivorous dinosaurs developed teeth and jaw structures that could process tough vegetation, including ferns, cycads, and conifer leaves that were common during the Jurassic Period. Some herbivores had teeth arranged in rows that could continuously replace worn surfaces, allowing them to feed on rough plant material without losing feeding efficiency. Carnivorous dinosaurs developed strong bite forces and sharp teeth that allowed them to capture and consume other animals. These feeding adaptations allowed dinosaurs to occupy different positions in the food chain and reduce direct competition between species with different diets. Body size variation was another important ecological advantage. Dinosaurs ranged from very small species to extremely large species. Small dinosaurs were able to hide, move quickly, and feed on small animals or insects. Larger dinosaurs were able to access higher vegetation and defend themselves against predators due to their size. The wide range of body sizes allowed dinosaurs to occupy multiple ecological levels within the same environment. This variation in size also meant that different species could coexist in the same region without directly competing for identical food sources or space. Reproductive strategies also contributed to ecological success. Dinosaurs laid eggs in relatively large numbers compared to some other land animals of the time. This allowed populations to grow quickly when environmental conditions were favorable. While not all eggs survived to adulthood, the number of offspring produced increased the chances that some individuals would reach maturity and reproduce. This reproductive pattern supported long-term population stability and expansion across different regions. The structure of dinosaur skin and body covering also contributed to ecological success. Most dinosaurs had tough, scaly skin that provided protection from environmental conditions and physical injury. This protective covering helped reduce water loss in dry environments and offered some defense against minor injuries from vegetation or interactions with other animals. Some dinosaurs may have also had early forms of insulating structures in certain groups, which could have helped regulate body temperature in changing environmental conditions. Although these features varied widely among species, they contributed to the ability of dinosaurs to live in a wide range of habitats. Occupation of major habitats was a key factor in the rise of dinosaur dominance. As dinosaurs diversified and developed ecological advantages, they began to spread into many different environments across land surfaces. Forested regions were one of the major habitats occupied by dinosaurs during the Jurassic Period. These forests contained a wide range of plant life, including tall conifers and cycads, which provided food for herbivorous dinosaurs. In these environments, plant-eating dinosaurs developed feeding strategies that allowed them to reach different levels of vegetation. Some fed on low-growing plants close to the ground, while others were able to feed on higher branches, due to their long necks or upright posture. Carnivorous dinosaurs in forested areas adapted to hunting in spaces with limited visibility, using movement and sensory abilities to locate prey among dense vegetation. Open floodplain environments were another major habitat occupied by dinosaurs. These areas were characterized by wide, flat land surfaces. With seasonal water flow, herbivorous dinosaurs often moved across these regions in search of food, following patterns of plant growth that changed with water availability. These environments supported large herds or groups of herbivorous dinosaurs in some regions, allowing them to feed on widespread plant resources. Carnivorous dinosaurs in floodplain areas adapted to covering large distances while searching for prey, taking advantage of open space to move efficiently and locate food sources. Coastal environments were also occupied by some dinosaur groups. These regions were influenced by nearby seas and often contained a mix of land and water-based ecosystems. Dinosaurs living in coastal regions had access to different types of vegetation and animal resources, compared to inland areas. Some species likely fed on plants growing in moist soil near water sources, while others may have taken advantage of animals that lived near shorelines. These environments required adaptations to changing water levels and shifting land conditions, and dinosaurs in these areas developed flexible movement and feeding behaviors that allowed them to survive in such changing surroundings. River systems and wetland environments provided another important habitat for dinosaurs. These areas contained constant water sources and rich plant growth, which supported large populations of herbivorous dinosaurs. Wetlands provided soft ground and dense vegetation, which influenced how dinosaurs moved and fed in these regions. Some dinosaurs developed body structures that helped them move through muddy or soft ground conditions. Predatory dinosaurs in these environments adapted to tracking prey along water channels and using cover provided by vegetation near riverbanks. Desert and dry environments were also occupied by some dinosaur species, although these areas were more challenging due to limited water and vegetation. Dinosaurs living in these regions developed behaviors and adaptations that allowed them to survive with fewer resources. They may have traveled long distances in search of food and water and relied on seasonal changes in plant growth. Their ability to survive in such conditions showed the wide ecological range that dinosaurs were able to occupy during the Jurassic Period. As dinosaurs spread across these habitats, they became integrated into nearly all major land ecosystems. Their presence influenced plant distribution, animal interactions, and the overall structure of ecosystems. Herbivorous dinosaurs shaped plant communities through feeding activities, while carnivorous dinosaurs influenced the behavior and movement of other animals. This interaction between different dinosaur groups and their environments continued to develop as dinosaur populations expanded and diversified further across time, forming a widespread and complex presence across Jurassic landscapes. Sauropods were some of the largest land animals that ever lived during the Jurassic period, and their presence shaped many parts of the ecosystems they occupied. They were long-necked, herbivorous dinosaurs that moved slowly or steadily across large areas of land while feeding on plant material. Their bodies were built in a way that supported great size, long necks, long tails, and strong pillar-like legs. These animals appeared as part of a long evolutionary process that began with earlier types of reptiles and early dinosaurs that slowly changed over many millions of years. The development of sauropods involved gradual changes in body structure, feeding habits, and movement patterns that allowed them to survive in different environments during the Jurassic period. The evolution of long-necked herbivores that later became sauropods began with early dinosaur ancestors that lived during the Triassic period. These early ancestors were generally smaller, lighter, and more flexible in movement compared to later sauropods. Over long periods of time, some of these early herbivorous dinosaurs began to develop features that supported a plant-based diet. These features included changes in teeth structure, neck length, and digestive systems. As plant life became more widespread and diverse during the Jurassic period, these herbivorous dinosaurs gradually adapted to feed more efficiently on large amounts of vegetation. The increase in plant availability created a condition where larger bodies became more useful for survival, since a larger digestive system could process more plant material. As time continued, certain groups of early herbivorous dinosaurs developed longer necks, which allowed them to reach vegetation at different heights. This adaptation reduced the need to move the entire body frequently, since the neck alone could cover a wide feeding area. Over many generations, these animals became more specialized in feeding on tall plants and trees, especially conifers and other tall Jurassic vegetation. The development of long necks was supported by changes in vertebrae structure. The bones in the neck became elongated and more numerous in some cases, and air-filled spaces developed inside the bones to reduce weight while still maintaining strength. This allowed the neck to grow longer without becoming too heavy for the body to support. The body size of these early long-necked herbivores also increased gradually. Larger body size provided advantages in storing food, digesting large quantities of plant material, and supporting long travel distances across changing landscapes. As the body grew larger, the legs also changed in structure. The limbs became more column-like, meaning they were positioned more directly under the body. This change helped support the weight of the growing body and allowed for more stable movement on land. The tail also became longer and stronger, helping balance the weight of the long neck and large body. During the Jurassic period, these evolutionary changes became more stable and resulted in the appearance of true sauropods. Sauropods developed a very specific body structure that included a very long neck, a long tail, a large body, and 4 strong legs that supported their weight. Their skulls were relatively small compared to their bodies, and their teeth were shaped for stripping leaves from plants rather than chewing tough food. Instead of chewing food thoroughly, sauropods swallowed large amounts of plant material, which was later broken down in the digestive system. The feeding strategies of sauropods were closely linked to their physical structure. Their long necks allowed them to reach a wide range of vegetation without needing to move their bodies frequently. This meant they could stay in one area and feed on plants across a large vertical range, from low-growing vegetation to tall tree branches. Different sauropod species adapted to different feeding heights, depending on neck length and body posture. Some species fed mostly on mid-level vegetation, while others specialized in feeding on the highest parts of trees. The teeth of sauropods were simple and often shaped like spoons or pencils, depending on the species. These teeth were not used for grinding food, but for stripping leaves and soft plant material from branches. Once the food was stripped, it was swallowed quickly. Inside the body, sauropods likely had very large digestive systems that included chambers where plant material could be broken down slowly over time. The process of digestion did not require heavy chewing, because the breakdown of plant material happened inside the gut through chemical and microbial processes. Sauropods needed to consume large amounts of food each day to support their massive bodies. Their feeding behavior was continuous or frequent, meaning they spent much of their time eating. The structure of their necks allowed them to access food without moving long distances, which reduced energy use. Some sauropods may have moved their necks in wide, sweeping motions to reach vegetation across a broad area, while others may have focused on specific feeding zones depending on their anatomy. Different sauropod species developed variations in feeding strategies based on their environment and body structure. Some species had extremely long necks that allowed them to feed at very high levels in forested areas. Others had shorter but still long necks that were more suited for feeding at medium heights. These differences allowed multiple sauropod species to live in the same general regions without directly competing for the exact same food sources. The major sauropod species of the Jurassic period included a wide variety of forms that existed in different parts of the world. One of the early and important groups included the diplodocids, which had extremely long necks and long whip-like tails. These dinosaurs had relatively light bodies compared to their length and were adapted for feeding over wide areas. Diplodocids included genera such as Diplodocus and Apatosaurus. Diplodocus had a very long, slender neck and a long tail that may have been used for balance and movement. Apatosaurus was more robust and heavier, with a thick body and strong limbs, but still maintained a very long neck used for feeding. Another major group of sauropods included the brachiosaurids. These dinosaurs had a different body structure compared to diplodocids. Brachiosaurids had longer front legs than back legs, which gave their bodies a more upward-sloping posture. This structure allowed them to reach very high vegetation levels. One of the most well-known members of this group is Brachiosaurus, which had a tall neck and a body built for high browsing. This adaptation allowed it to feed on vegetation that was out of reach for many other herbivores of the same time. Camarasaurids were another important group of sauropods that lived during the Jurassic period. These dinosaurs had shorter necks, compared to diplodocids and brachiosaurids, but still maintained large body sizes. Their skulls were more robust and their teeth were stronger, allowing them to handle tougher plant material. Camarasaurus is one of the most studied members of this group, and it shows a strong body with a relatively shorter neck that was still effective for feeding at medium heights. Mamenchisaurids were especially notable for having extremely long necks, sometimes longer than those of other sauropods. These dinosaurs lived mainly in parts of Asia and showed a strong specialization in reaching high vegetation. Mamenchisaurus is one of the best-known examples of this group. Its neck made up a very large portion of its total body length, and its structure suggests that it could access plant material from a wide, vertical range without moving its body frequently. Shunosaurus and other similar sauropods from the Jurassic period also played important roles in the diversity of sauropod species. These dinosaurs were generally smaller compared to the larger sauropods, but still had the typical long neck and herbivorous feeding habits. They contributed to the overall diversity of sauropod life by occupying different ecological roles and feeding areas. Sauropods were spread across many regions of the world during the Jurassic period, and their fossils have been found in North America, Africa, Asia, and Europe. Their wide distribution shows that they were highly successful in adapting to different environments. The structure of their bodies allowed them to survive in areas with different types of vegetation and climate conditions. Their ability to process large amounts of plant material made them efficient at using the available resources in their environments. The growth patterns of sauropods also played an important role in their evolution. Many sauropods grew rapidly during early stages of life, which allowed them to reach large sizes in a relatively short period of time. As they grew, their bodies changed shape, with the neck, legs, and tail developing in coordination with overall body size. This growth pattern required a high intake of food, which is why their feeding strategies were closely linked to their physical development. The reproduction of sauropods involved laying eggs, which were often placed in nests on the ground. Fossil evidence suggests that some sauropods laid many eggs at once, increasing the chance that some offspring would survive to adulthood. The young sauropods were much smaller than adults and likely had different feeding habits due to their size and ability to reach different vegetation levels. As they grew, their feeding range expanded along with their neck length and body size. The skeletal structure of sauropods shows many adaptations for supporting large bodies. Their bones were often filled with air spaces, which reduced weight without reducing strength. This adaptation was important for supporting long necks and large bodies while still allowing movement on land. The vertebrae of the neck and back were designed to provide both flexibility and strength, allowing the animals to move their necks while maintaining stability. The movement of sauropods was generally slow to moderate, but their large stride length allowed them to cover significant distances when needed. Their legs acted like strong pillars that supported their weight, and their joints were structured to handle stress from constant movement and standing. The tail helped balance the body and may also have been used in movement adjustments. Sauropods interacted with their environment mainly through feeding, movement, and growth. Their constant feeding shaped plant distribution in some areas as they consumed large amounts of vegetation. Their presence influenced the structure of Jurassic ecosystems, especially in regions where they were abundant. Their fossils provide important information about the types of plants that existed during the Jurassic period, as well as the environments in which they lived. The long evolutionary history of sauropods shows a continuous development of body structures and feeding strategies that allowed them to become some of the most successful herbivorous dinosaurs of the Jurassic period. Stegosaurs and other herbivorous dinosaurs that lived during the Jurassic period were among the most widely distributed plant-eating reptiles of their time, and they played a major role in shaping land ecosystems through their feeding habits, body structures, movement patterns, and interactions with plants and other animals. These dinosaurs existed in many different forms, ranging from heavily armored species with plates or spikes to lighter-bodied plant-eaters with long necks or strong beaks designed for stripping vegetation. Their physical characteristics were closely tied to their survival needs in environments filled with large predators and changing plant life. And these characteristics also influenced how they moved, how they fed, and how they survived across different landscapes that existed during the Jurassic period. Herbivorous dinosaurs were not a single uniform group, but instead a wide range of species that shared the basic dietary habit of eating plants, while showing many different body structures that supported this lifestyle. Among the most well-known of these herbivorous dinosaurs was Stegosaurus, which had a distinct body form that included a small head, a heavily built body, a row of large plates along its back, and a tail equipped with pointed spikes. The physical characteristics of Stegosaurus were shaped by the need to process large amounts of plant material, while also dealing with threats from large carnivorous dinosaurs. The head of Stegosaurus was relatively small in relation to its body size, and it contained a beak-like structure at the front of the mouth that was used to bite off plant material. Behind the beak, the teeth were small and suited for breaking down soft vegetation, rather than chewing tough plant fibers. The neck of Stegosaurus was moderately long and allowed the animal to reach vegetation at different heights, although it mainly fed on low-growing plants. The body of Stegosaurus was broad and supported by strong limbs. The hind legs were longer and stronger than the front legs, giving the body a sloped appearance from the hips to the shoulders. The digestive system inside the body was large and capable of processing plant material slowly, allowing nutrients to be extracted over time. Other herbivorous dinosaurs of the Jurassic period showed different physical characteristics depending on their feeding habits and environments. Many of these dinosaurs had long necks that allowed them to reach vegetation that grew at higher levels above the ground. These long-necked herbivores had small heads and simple teeth structures that were not designed for chewing in a complex way, but were instead used to strip leaves and plant material. Their bodies were often large and supported by thick, column-like legs that carried their weight. The structure of their vertebrae allowed flexibility in the neck while maintaining strength to support long feeding ranges. The tail in many of these dinosaurs served as a counterbalance to the long neck, helping to stabilize movement while walking or standing. Other herbivorous dinosaurs had beaked mouths that allowed them to crop vegetation efficiently. These beaks were often made of hard keratin and were shaped in ways that allowed precise feeding on specific plant parts. Behind the beak, some of these dinosaurs had batteries of teeth that were constantly replaced throughout their lives. These teeth were arranged in rows and allowed continuous processing of plant material. The jaw structure of these herbivores was adapted for repetitive movement that ground plant material into smaller pieces that could be digested more easily. The skulls of these dinosaurs were often light compared to their body size, which helped reduce the energy needed for movement. The skin and outer coverings of herbivorous dinosaurs varied widely. In some species, the skin was thick and covered with bony structures embedded within it, while in others, the skin was smoother but still tough enough to protect against injuries from plants or predators. The body surface of these dinosaurs often included ridges, knobs, or other structures that added protection and support. In species like Stegosaurus, large plates rose from the back in a vertical arrangement along the spine. These plates were made of bone covered by a layer of skin, and they were deeply embedded into the body, connecting to blood vessels and internal tissues. The arrangement of these plates followed a pattern from the neck to the tail, becoming smaller or changing shape along the way. The tail structures of some herbivorous dinosaurs were also highly developed. In Stegosaurus, the tail ended in pairs of long spikes that extended outward and backward. These spikes were part of the skeletal structure and were covered in keratin, making them strong and resistant to damage. The tail was muscular and flexible, allowing movement in different directions. In other herbivorous dinosaurs, the tail was long and heavy, used for balance and sometimes for movement support while feeding. The vertebrae in the tail region were connected in a way that allowed controlled motion while maintaining structural strength. The defensive adaptations of herbivorous dinosaurs were closely connected to their environment and the presence of large predators. Many herbivores developed physical features that reduced the chance of being attacked or that increased their ability to defend themselves when necessary. In Stegosaurus, the large plates along the back may have served multiple roles, including protection of the spine and surrounding tissues. The plates were arranged in alternating rows, which created a protective barrier along the upper body. The tail spikes of Stegosaurus were used as active defensive tools, capable of being swung toward attackers. The combination of a strong tail and sharp spikes allowed this dinosaur to respond to threats coming from behind or from the sides. Other herbivorous dinosaurs relied on body size as part of their defense. Large bodies made it difficult for predators to attack them successfully, especially when the herbivores were fully grown. The thickness of the skin in some species also provided resistance to bites or scratches. Some dinosaurs developed bony plates embedded in their skin, known as osteoderms, which acted as internal armor. These structures were located in different parts of the body depending on the species, including the back, neck, and tail regions. In some cases, clusters of these bony structures formed protective layers that absorbed impact from external forces. Some herbivorous dinosaurs also had strong limbs that allowed them to move quickly when necessary. The structure of the legs in these animals was adapted for carrying heavy bodies and maintaining balance during movement. The joints in the legs allowed forward and backward motion, and the bones were thick enough to support sustained walking across long distances. In some herbivores, the front limbs were shorter than the hind limbs, which influenced posture and movement patterns. The feet of these dinosaurs were shaped in ways that allowed them to distribute weight evenly across the ground. The skull structures of herbivorous dinosaurs also contributed to defensive strategies. Some species had thick skull bones that protected the brain and sensory organs. Others had narrow skulls with reinforced areas that could withstand impact. The placement of the eyes on the sides of the head in many herbivorous dinosaurs allowed a wide field of vision, which helped in detecting approaching predators. The nostrils and sensory structures in the head also played a role in environmental awareness, allowing these animals to respond to changes in their surroundings. Feeding strategies of herbivorous dinosaurs were closely linked to their physical features and defensive adaptations. These dinosaurs consumed a wide range of plant materials, including leaves, stems, ferns, cycads, and other vegetation that existed during the Jurassic Period. The way they fed depended on the structure of their mouths, teeth, and necks. Some herbivores fed close to the ground, stripping low vegetation, while others fed at different heights depending on neck length and posture. The digestive systems of these animals were adapted to process large amounts of plant material over long periods of time. Many herbivorous dinosaurs had large gut chambers where plant matter was broken down slowly with the help of internal processes. The movement patterns of herbivorous dinosaurs were shaped by their need to find food, avoid predators, and move across different environments. Some species moved in groups while others may have moved alone or in small numbers, depending on environmental conditions and resource availability. The limbs of these dinosaurs were structured to support steady movement rather than fast running in most cases, although some could move more quickly when needed. The joints in the limbs allowed for repeated walking motions that supported long-distance travel across land areas that included forests, open spaces, and regions with dense plant growth. The role of herbivorous dinosaurs in Jurassic ecosystems was deeply connected to their feeding habits and population distribution. By consuming large amounts of plant material, these dinosaurs influenced the growth patterns of vegetation across different regions. Their feeding activities affected the structure of plant communities by removing certain types of plants and allowing others to grow in their place. The constant feeding pressure from large herbivores influenced the density and spread of plant life in many environments. Herbivorous dinosaurs also served as a major food source for carnivorous dinosaurs. The presence of large herbivores supported the existence of large predators, which depended on them for survival. This relationship influenced the distribution and behavior of both groups. Herbivores often needed to remain alert and aware of their surroundings while feeding or moving, which influenced their sensory development and defensive behaviors. The physical movement of herbivorous dinosaurs across landscapes also contributed to the shaping of environments. As they moved, they trampled vegetation and created paths through dense plant growth. These paths could later be used by other animals moving through the same regions. Their feeding and movement patterns also influenced soil conditions in some areas by disturbing plant cover and exposing ground surfaces. The reproduction of herbivorous dinosaurs involved laying eggs, which were often placed in nests or protected areas depending on the species. Some dinosaurs may have shown forms of nesting behavior where eggs were grouped together in specific locations. The growth of young herbivores required access to food sources and protection from predators, and their early development stages involved changes in body structure as they grew into adult forms. The diversity of herbivorous dinosaurs during the Jurassic period included many different body forms and adaptations that allowed them to survive in a wide range of environments. Some had thick protective bodies with armor-like features. Others had long necks and feeding structures adapted for reaching high vegetation, and others had beaks and teeth suited for processing plant material efficiently. The presence of these different forms allowed herbivorous dinosaurs to occupy many ecological roles across land environments. The interaction between herbivorous dinosaurs and plant life also influenced the evolution of plants during the Jurassic period. Plants developed structures that could resist feeding pressure, such as tougher leaves or protective features, while herbivores adapted to these changes by developing stronger feeding mechanisms or different feeding strategies. This ongoing interaction shaped the development of both plant and animal life across long periods of time. The skeletal structure of herbivorous dinosaurs was a key factor in their survival. Bones had to support large body weights and allow movement across different terrains. The vertebral column supported the body from head to tail and provided attachment points for muscles. The ribcage protected internal organs, including the digestive system, which was essential for processing plant material. The pelvis and shoulder regions were strongly built to support limb movement and body stability. The nervous systems of herbivorous dinosaurs allowed them to process information from their environment, including visual, olfactory, and auditory signals. These sensory inputs helped them detect food sources and potential threats. The brain size in relation to body size varied among different species, but it was generally sufficient to coordinate movement, feeding, and basic survival behaviors. The daily activity patterns of herbivorous dinosaurs involved periods of feeding, movement, and rest. Feeding likely occupied a large portion of their time due to the need to consume significant amounts of plant material to maintain energy levels. Movement between feeding areas required energy expenditure that was balanced by food intake. Rest periods allowed for digestion and recovery. The environment in which herbivorous dinosaurs lived included forests, open land areas, and regions with varied plant density. These environments changed over time due to geological and climatic factors that influenced the availability of vegetation. Herbivorous dinosaurs adapted to these changes through shifts in feeding patterns and movement across different regions. The structure of herbivorous dinosaur communities included multiple species living in the same general areas, while occupying different feeding zones or ecological roles. This distribution allowed different species to access different types of vegetation and reduce direct overlap in feeding behavior. The presence of multiple herbivorous species in the same environment influenced the overall structure of plant communities and animal interactions. The life cycle of herbivorous dinosaurs involved growth from eggs to juvenile forms and then to fully developed adults. Growth stages included changes in body size, limb strength, and feeding ability. Juveniles often had different survival challenges compared to adults, including greater vulnerability to predators and limited feeding capacity. As they matured, their physical structures became more suited to long-term survival and reproduction. Herbivorous dinosaurs maintained a continuous presence in Jurassic ecosystems, influencing both living and non-living components of their environments through their physical activities, feeding behavior, and movement patterns across land surfaces, shaping the distribution of plant life, the behavior of predators, and the overall structure of terrestrial ecosystems in ways that extended across large regions and long spans of time. Predatory dinosaurs of the Jurassic period lived during a long stretch of Earth's history, when large land reptiles became widely spread across many environments. These carnivorous dinosaurs developed over millions of years, slowly forming different body structures, survival habits, and feeding methods that allowed them to live by hunting other animals. Their evolution was shaped by changing climates, shifting land surfaces, and the growing diversity of plant-eating dinosaurs that became their main source of food. Over time, different groups of meat-eating dinosaurs appeared, each with their own physical form and ways of finding and capturing prey. The evolution of large carnivorous dinosaurs during the Jurassic period began from smaller, early theropod ancestors that already existed in the earlier Triassic period. These early ancestors had light bodies, long tails, and sharp teeth that allowed them to feed on smaller animals and sometimes on weak or injured larger animals. As time passed into the Jurassic period, some of these theropod lineages increased in body size. Their bones became stronger, their skulls became larger, and their teeth became more specialized for cutting through flesh. These changes did not happen suddenly but through many generations, as environmental conditions and food availability guided their development. During the Jurassic period, the Earth had many regions filled with plant life, which supported large populations of herbivorous dinosaurs. This increase in plant-eating dinosaurs created a steady source of food for carnivorous dinosaurs. As a result, predatory dinosaurs adapted to take advantage of these available food sources. Their bodies developed strong jaw muscles, curved claws on their feet and hands, and flexible necks that allowed them to move quickly and strike at prey. Their tails became important for balance, especially when running or turning during movement. Some species developed strong hind legs that allowed them to move with speed across open land, while others became more powerful in their upper body for gripping and holding prey. The skull structure of Jurassic predatory dinosaurs became an important part of their evolution. Many of these dinosaurs had long skulls filled with sharp teeth that were shaped like blades. These teeth were not designed for chewing, but for tearing flesh into pieces that could be swallowed. The arrangement of teeth varied among different species, but most had teeth that were curved backward, helping them hold on to struggling prey. Some species also had openings in their skull bones that reduced weight while keeping the structure strong enough to handle pressure during feeding. The eyes of these carnivorous dinosaurs were generally positioned in a way that allowed them to focus on objects in front of them. This helped them detect movement in their environment, especially the movement of plant-eating dinosaurs that were potential food sources. Their sense of smell also played an important role. Some species had nasal structures that allowed them to detect scents over distance, which helped them locate dead animals or living prey hidden in vegetation. Hearing abilities in some species were also developed enough to pick up sounds of movement in their surroundings. The skin of predatory dinosaurs during the Jurassic period was covered with scales in most species. These scales provided protection against injury during movement through rough terrain or during physical struggle with prey. In some smaller or more specialized species, there may have been simple feather-like structures, although this was not common in the large carnivorous dinosaurs of the period. The coloration of their skin is not fully known, but it likely varied depending on habitat, with some forms possibly having patterns that helped them blend into forested or open environments. The hunting behavior of Jurassic predatory dinosaurs was influenced by their physical structure and the environment they lived in. Many of these dinosaurs likely relied on movement-based hunting strategies. They would observe their surroundings and wait for opportunities when herbivorous dinosaurs were isolated, injured, or distracted. Once a target was identified, they could move in quickly using strong hind limbs and coordinated body motion. The tail helped maintain balance during rapid movement, especially when turning or adjusting direction. Some predatory dinosaurs may have used short bursts of speed rather than long continuous chases. This means they would approach carefully and then use sudden acceleration to close distance with prey. Their claws were important tools during hunting. The claws on their hands could be used to grip or hold on to prey animals, while the claws on their feet helped with stability and movement on different ground surfaces. Once contact was made, the dinosaur would use its jaws to bite into the body of the prey animal. There is also evidence that some Jurassic carnivorous dinosaurs may have engaged in opportunistic feeding. This means they would sometimes feed on animals that were already dead, rather than actively hunting them. This behavior would help them survive during times when hunting conditions were not favorable. Feeding on carcasses would also reduce the energy needed to obtain food. Their strong sense of smell would assist in locating such food sources. Social behavior among predatory dinosaurs during the Jurassic period is not fully clear, but some fossil evidence suggests that certain species may have lived or hunted in loose groups. If this occurred, it could have allowed them to take down larger prey animals or share food resources. However, not all species would have behaved in this way, and many likely lived and hunted alone. The structure of their bones and fossil trackways sometimes suggests movement patterns that indicate more than one individual in the same area at the same time. One of the major predatory dinosaur groups of the Jurassic period includes Allosaurus. This dinosaur lived during the late part of the Jurassic period and was one of the more widely distributed large carnivores. It had a large skull filled with sharp teeth and strong jaw muscles. Its arms were relatively small but still carried claws that could assist in holding prey. Its hind legs were strong, supporting fast movement and sudden directional changes. Allosaurus likely fed on large herbivorous dinosaurs and may have also scavenged when opportunities were available. Its skull had openings that made it lighter, while still maintaining strength for biting actions. Another important Jurassic predator was Ceratosaurus. This dinosaur had a distinct horn-like structure on its snout, which made its skull appear different from other carnivorous dinosaurs of the time. Ceratosaurus had a long body and strong tail that helped it move through its environment. Its teeth were sharp and curved, suitable for cutting into flesh. Fossil evidence suggests that Ceratosaurus lived in areas where water sources were present, and it may have hunted near rivers or wetlands where plant-eating dinosaurs gathered to drink or feed. Megalosaurus is another early large predatory dinosaur that lived during the Jurassic period. It is one of the first dinosaurs to be scientifically described in modern times. Megalosaurus had a strong jaw filled with teeth that were used for feeding on large animals. Its body structure suggests it was capable of both movement on land and strong physical engagement with prey. It lived in environments that had a mix of forested areas and open spaces, giving it access to different types of prey animals. Torvosaurus was another large carnivorous dinosaur that existed during the Jurassic period. It had a very strong jaw and large teeth designed for biting through thick flesh. Its body was powerful and supported by strong legs that allowed movement across different terrains. Torvosaurus is known from fossil remains found in both North America and Europe, suggesting it lived in different regions that had similar environmental conditions during the Jurassic period. Its feeding behavior likely involved attacking large herbivorous dinosaurs and consuming available meat resources. Piatnitskysaurus is a smaller but still significant predatory dinosaur from the Jurassic period. It had a lighter body structure compared to some of the larger carnivores, which may have allowed it to move more quickly in certain environments. Its skull was equipped with sharp teeth, suitable for capturing smaller dinosaurs or juvenile individuals of larger species. It lived in regions that included forested environments and open land areas where prey was available. The evolution of hunting behavior in Jurassic predatory dinosaurs was closely linked to their physical development. As their bodies became more adapted to capturing and processing meat, their methods of hunting became more effective. Some species developed stronger bite forces, allowing them to break through thick skin and muscle tissue. Others relied more on speed and agility to catch prey before it could escape. These different strategies developed across species depending on their body size, habitat, and available prey types. The feeding process of these carnivorous dinosaurs involved tearing flesh into manageable pieces. Since most of them did not chew food in the way modern mammals do, they relied on swallowing chunks of meat. Their digestive systems were adapted to break down large amounts of protein from animal tissue. Some evidence suggests that certain species may have used their teeth in a way that allowed them to pull meat away from bone more efficiently. Juvenile predatory dinosaurs likely had different feeding behaviors compared to adults. Younger individuals may have focused on smaller prey due to their size and strength limitations. As they grew, their diet would gradually shift toward larger animals. This change in feeding pattern would also be accompanied by changes in jaw strength, tooth size, and overall body structure. Environmental factors during the Jurassic period also influenced predatory dinosaur behavior. Forested regions provided cover for ambush-based movement, while open areas allowed for more active pursuit of prey. Water sources attracted large groups of herbivorous dinosaurs, making them important locations for feeding activity. Seasonal changes may have influenced movement patterns, as some areas became more or less suitable for sustaining prey populations. The sensory abilities of Jurassic carnivorous dinosaurs played a key role in their survival. Vision helped them detect movement at different distances. Smell helped them locate food sources that were not visible. Hearing allowed them to detect movement or disturbance in vegetation or water. These combined senses created a system that supported their feeding and survival needs in a wide range of environments. Bone fossils of predatory dinosaurs show evidence of growth patterns that reflect changes over time. Growth rings in bones indicate periods of faster and slower development, which may be linked to environmental conditions and food availability. Injuries found on some fossil specimens suggest that these animals sometimes experienced physical struggles either with prey or with other predators. Some healed injuries show that they survived such encounters and continued living afterward. Egg fossils and nesting sites provide information about early life stages of these dinosaurs. Although adult predatory dinosaurs were large and powerful, hatchlings were small and vulnerable. They likely depended on hiding or rapid growth to avoid becoming prey themselves. As they developed, their hunting skills and physical strength increased gradually. The distribution of major predatory dinosaur species across Jurassic environments shows that they occupied many different ecological regions. Some lived in coastal areas, others in inland forests, and others in regions with mixed terrain. This wide distribution reflects their ability to adapt to different conditions and prey availability. Fossil evidence of tooth marks on bones of herbivorous dinosaurs provides direct indication of feeding activity by carnivorous dinosaurs. These marks show patterns consistent with biting and tearing actions. In some cases, multiple marks on a single bone suggest repeated feeding activity at the same location. Trackway fossils also provide evidence of movement behavior. These trackways show footprints left behind by walking or running dinosaurs. The spacing and depth of footprints can indicate movement speed and body weight. Some trackways suggest that multiple carnivorous dinosaurs may have been present in the same area at the same time. The anatomical structure of Jurassic predatory dinosaurs reflects their adaptation to a life dependent on meat consumption. Their muscles, bones, and joints work together to support movement, hunting, and feeding. Their tails acted as stabilizing structures, their legs supported locomotion, and their arms assisted in handling prey. Their heads were specialized for biting and tearing food. Growth and development patterns in these dinosaurs continued throughout much of their lives. As they aged, their body structures became more robust, and their hunting abilities became more refined. Changes in tooth wear patterns show that feeding activity was continuous and involved repeated use of teeth in processing food. Different species of predatory dinosaurs coexisted during the Jurassic period, occupying different ecological roles based on their size, strength, and feeding behavior. Some focused on large prey, while others targeted smaller animals or juvenile individuals. This distribution of feeding behavior allowed multiple species to exist in the same general environment without relying on identical food sources in all situations. The early development of birds began deep in the time of dinosaurs. when life on land was already filled with many forms of reptiles that moved across different environments and occupied many ecological roles. During the later part of the Mesozoic time, especially around the late Jurassic period, living creatures that would later be recognized as early birds began to appear from within a group of dinosaurs known as theropods. These theropods were a large group of mainly carnivorous dinosaurs that moved on two legs and had bodies designed for active movement. Over long periods of time, measured in millions of years, some of these theropods began to develop features that later became important in birds. These changes did not appear suddenly, but developed gradually through many generations as small variations in body structure were passed on. The origin of early birds from theropod dinosaurs is understood through fossil evidence that shows gradual changes in bone structure, body covering, and limb formation. Theropod dinosaurs had many forms, ranging from large predators to smaller and more agile species. Among the smaller forms, some had bodies that were light in structure and they moved quickly across the ground. Their bones were often hollow or partially hollow, which reduced body weight and supported movement. Over long periods of time, some of these dinosaurs began to show changes in their forelimbs. These forelimbs slowly developed structures that later supported feather growth and different types of movement. Feathers first appeared in theropod dinosaurs before the existence of true birds. Early feathers did not serve the purpose of flight. Instead, they likely had roles related to body covering, temperature control, and display behavior. Fossil evidence shows that feather-like structures were present in several groups of theropods. These structures were simple in form at first, consisting of thin filaments emerging from the skin. Over time, these filaments became more complex, forming branching structures. The development of feathers involved gradual biological changes, where skin cells began producing keratin in new forms, allowing more structured and organized growth. The development of feathers continued over many generations, and different types of feather structures appeared in different species. Some feathers remained simple and filament-like, while others became more branched and structured. These developments were not uniform across all theropods, but appeared in various forms depending on species and environmental conditions. The presence of feathers in non-bird theropods shows that feathers originally had functions unrelated to flight. They may have helped regulate body temperature by providing insulation. In some species, feathers may have also played a role in visual signaling during social behavior. As time progressed, changes in bone structure and feather arrangement became more connected. The forelimbs of some theropods became more flexible and developed a range of motion that allowed greater control. The arrangement of bones in the shoulder region also changed, allowing improved movement of the forelimbs. These changes supported the growth of longer and more structured feathers on the arms and tail. The development of these features took place over a long period of time in the late Jurassic, which occurred around 150 million years ago. The emergence of early bird-like creatures is strongly associated with fossils found from this time period. One of the most important fossils discovered is known as Archaeopteryx. This organism lived during the late Jurassic period and shows a combination of features found in both dinosaurs and birds. Its fossil remains show impressions of feathers along the wings and tail, along with skeletal features that are similar to theropod dinosaurs. The structure of its skull, teeth and claws reflects characteristics that were present in its dinosaur relatives. The body structure of Archaeopteryx shows that it had wings formed by long feathers attached to its forelimbs. These feathers were arranged in a pattern that allowed movement in the air. The tail contained long feathers extending from a bony structure, which provided stability during movement. The hands of this organism had clawed fingers, which were similar to those found in theropod dinosaurs. These features showed that early birds retained many ancestral traits while also developing new structures related to flight. The skull of Archaeopteryx contained teeth rather than a beak. These teeth were small and sharp, arranged along the jaws. This feature shows a clear connection to theropod dinosaurs, which also had teeth. The presence of teeth in early bird-like organisms indicates that the transition toward modern bird features occurred gradually, with different traits changing at different times. The brain structure of early birds was also in a developing stage, with certain areas beginning to show changes related to sensory processing and movement coordination. Feather development in early birds became more advanced in organisms such as Archaeopteryx. The feathers on the wings were long and structured, with a central shaft and smaller branches extending outward. These feathers were arranged in a pattern that allowed air movement across the wing surface. The feathers on the tail also had a structured arrangement, forming a surface that helped with balance and control. The presence of such feathers shows that feather development had reached a level where they could support movement through air, even though powered flight may not have been fully developed in all behaviors. The origins of early birds from theropod dinosaurs involve many stages of biological change that took place across long periods of time. The skeletal system of theropods underwent modifications that supported lighter body weight. Bone cavities became more pronounced, and internal structures of bones changed in ways that reduced overall mass while maintaining strength. These changes allowed greater mobility of the forelimbs and improved balance during movement. The vertebral column in theropod dinosaurs also experienced gradual changes. The connection between vertebrae in different regions of the body became more specialized. The tail region in particular played an important role in balance and movement. In early bird-like organisms, the tail structure began to shorten in later stages of evolution. But in earlier forms, such as Archaeopteryx, the tail remained long and flexible, supporting feather arrangement and movement control. The development of feathers involved biological processes within the skin, where specialized cells began producing keratin in new structural patterns. These cells formed follicles from which feather structures emerged. The branching patterns of feathers became more complex as genetic changes influenced growth patterns. Over time, feathers developed central shafts known as rachis structures, with smaller branches extending outward. These branches created surfaces capable of interacting with air movement, temperature regulation, and visual display. The distribution of feathers across the body of early bird-like organisms was not limited to the wings. Fossil evidence shows that feathers covered multiple regions of the body, including the arms, tail, and possibly parts of the torso. The distribution pattern suggests that feathers first appeared as body coverings before being adapted for additional functions. In organisms such as Archaeopteryx, feathers were clearly present on the wings and tail, showing a stage where feather structure had expanded into multiple functional areas. The environment in which early bird evolution took place during the late Jurassic Period consisted of diverse landscapes that included forested regions, open areas, and regions near water bodies. These environments supported many types of reptiles, insects, and early mammals. The presence of diverse ecological conditions provided opportunities for different forms of adaptation. Small theropod dinosaurs that lived in these environments had access to various food sources and habitats, which supported gradual changes in body structure and behavior over long periods of time. The fossil record of early birds shows that the transition from non-bird theropods to early birds involved many intermediate forms. These forms show combinations of traits, including dinosaur-like skeletal structures and bird-like feather arrangements. The study of these fossils provides evidence that early bird evolution did not involve sudden changes, but involved gradual development of features across many generations. The appearance of Archaeopteryx represents one of the earliest known examples of this combination of features preserved in fossil form. The forelimbs of theropod dinosaurs that gave rise to birds underwent significant structural modification. The bones in the arm region became lighter and more adapted for movement in multiple directions. The joints in the shoulders allowed a wider range of motion, which supported the positioning of feathers. The fingers in some species remained separate and clawed, as seen in early forms such as Archaeopteryx. These claws may have supported climbing or grasping movements, showing that early bird-like organisms still retain functional traits from their dinosaur ancestors. The development of feathers also involved changes in pigmentation and texture. Fossil evidence sometimes preserves traces of color patterns in feather structures, indicating that feathers may have had visual functions in addition to structural roles. The microstructure of feathers shows arrangements that reflect different types of keratin organization. These microstructures influenced flexibility, strength, and surface texture of feathers. The nervous system of early bird-like organisms began to show changes related to movement control and sensory processing. The coordination of limb movement became more refined, as forelimbs developed more complex feather arrangements. The brain regions associated with vision and movement coordination gradually expanded in relation to changes in behavior and movement patterns. These changes supported more precise control of body movement in air or in elevated environments. The reproductive behavior of early birds also shows continuity with theropod dinosaurs. Eggs laid by theropod dinosaurs had structures similar to those found in later bird species. Nesting behavior likely developed gradually, with some theropods showing evidence of nesting in groups or caring for eggs. These behaviors provided conditions that supported survival of offspring and allowed gradual transmission of traits over time. The study of Archaeopteryx continues to provide important information about the early stages of bird evolution. Its fossil remains show clear preservation of feather impressions, along with skeletal details that connect it to theropod dinosaurs. The combination of features found in this organism helps explain the gradual changes that occurred during the transition from ground-dwelling dinosaurs to early bird-like forms. The structure of its wings, tail, and body provides insight into the development of early flight-related features and body adaptations. The evolutionary changes that led to early birds involved many interconnected biological processes, including skeletal modification, feather development, changes in skin structure, and gradual changes in movement ability. These processes took place over long periods of time during the late Jurassic period. The fossil record continues to show evidence of intermediate stages that link theropod dinosaurs with early bird-like organisms, including forms such as Archaeopteryx, which preserves many of these early characteristics in a single organism. Geological activity during the Jurassic period was very active and involved many changes happening inside the Earth and on the surface of the land. These changes shaped the land slowly over very long periods of time. The processes included volcanism, mountain building, and rift formation that led to continental breakup. Each of these processes worked through natural forces deep within the Earth and affected the arrangement of land and sea across the planet during that time. Volcanism during the Jurassic period involved the movement of molten rock from deep inside the Earth toward the surface. This molten rock is called magma when it is below the ground, and lava when it reaches the surface. During the Jurassic, magma moved through cracks and weak zones in the Earth's crust. When pressure built up under the surface, it caused eruptions that released lava, ash, and gases. These volcanic materials spread over land areas and sometimes into shallow seas. Over long periods of time, layers of lava cooled and became solid rock, forming large volcanic rock formations. Volcanic activity during this period was not limited to one type of eruption. Some eruptions were steady and slow, where lava flowed out over time and covered wide areas. Other eruptions were sudden and released large amounts of material in a short time. Ash from volcanic eruptions spread through the air and settled over land and water, forming thin layers that later became part of the rock record. These layers helped scientists understand the timing of volcanic events during the Jurassic. Volcanism also released gases into the atmosphere which influenced the chemical composition of the air. These gases included carbon dioxide and water vapor, which came from deep within the Earth. Volcanism was closely connected to the movement of tectonic plates. As the plates moved, cracks formed in the crust, allowing magma to rise more easily. In some areas, volcanic activity created large plateaus, made from repeated lava flows. In other areas, volcanic vents created cones and other structures built from accumulated lava and ash. Over long periods of time, these volcanic structures changed the shape of the land surface. Mountain building during the Jurassic Period happened when large sections of the Earth's crust were pushed together by tectonic forces. These forces caused layers of rock to bend, fold, and break. As pressure continued, parts of the crust were lifted upward, forming mountain ranges. This process took place slowly and continued over millions of years. Rocks that were once deep underground were pushed toward the surface during this activity. The formation of mountains involved strong pressure that caused rocks to change their position and structure. Some rocks were folded into curved shapes, while others broke and shifted along fault lines. Heat from deep within the Earth also affected these rocks, causing changes in their physical structure. Mountain building did not happen in a single event, but occurred in stages as tectonic plates continued to move. During the Jurassic Period, mountain building affected large areas of the Earth's surface. As landmasses shifted, some regions were pushed upward, while others were lowered. This created differences in elevation across continents. Rivers and other natural processes later shaped these newly formed highlands by cutting through them and carrying away rock material. Sediments from these processes were deposited in lower areas, forming new layers of sedimentary rock over time. Rift formation during the Jurassic Period involved the stretching and pulling apart of the Earth's crust. This process occurred when tectonic forces caused the crust to become thinner and weaker in certain regions. As the crust stretched, large cracks developed. These cracks gradually widened, creating rift zones. In these zones, blocks of land could sink or rise depending on how the crust moved. Rift formation was an important process because it marked the beginning stages of continental breakup. As rifts expanded, they created deep valleys and basins that could later be filled with water or sediments. These basins often became sites where lakes or shallow seas formed. The movement of magma also increased in rift zones because the crust was thinner and easier for molten rock to pass through. Continental breakup during the Jurassic Period occurred as a result of continued rifting and movement of tectonic plates. Large landmasses that were once joined together began to separate slowly. This separation happened over millions of years as rift zones expanded into wider gaps. As the land split apart, new ocean areas began to form between the separating continents. The process of continental breakup involved both horizontal and vertical movement of the Earth's crust. Horizontal movement caused land to drift apart, while vertical movement created changes in elevation along the edges of the separating landmasses. These movements were driven by heat and energy from inside the Earth, which caused convection currents in the mantle. These currents slowly moved the tectonic plates above them. As continents broke apart, the shapes of coastlines changed. New ocean basins formed where land once existed. Sediments filled these basins over time, carried by rivers and erosion from nearby land areas. Volcanic activity often increased along the edges of separating continents due to the thinning of the crust. This added more layers of volcanic rock to these regions. The combined effect of volcanism, mountain building, and rift formation during the Jurassic period led to continuous changes in the Earth's surface. These processes worked together over long periods of time, shaping the arrangement of land and sea. The crust was constantly being built up in some places and broken down in others. Rocks were moved, buried, exposed, and transformed as geological activity continued. In many regions, volcanic activity and mountain building occurred at the same time, especially where tectonic plates interacted strongly. Rift zones also influenced where volcanic activity happened, since magma could rise more easily in stretched and weakened crust.